Good evening, welcome to this video for the 2020 Level 3 Electricity paper for Level 3 Physics. So let's get straight into it. So question 1, AC circuits. Tui is investigating LCR circuits. She sets up the circuit shown below using a signal generator and sets the supply voltage to 65 volts RMS voltage, 50 Hz. Frequency is 50 Hz. Calculate the peak voltage of the supply. So we know that the peak voltage is equal to RMS voltage times by root 2. So peak voltage equals to the RMS voltage times root 2. So therefore, the peak voltage is equal to 65 times root 2, which comes out to be 91.9 volts, which equals to 91.9 volts. That should just be an achievable question, so achieved here. Question B, the supply voltage in the circuit above leads the circuit current by 35 degrees. The resistor has a resistance of 150 ohms. Calculate the total impedance of the circuit. Alright, so this question we know that the resistor is in phase of the current and the impedance is in phase of the supply voltage. So therefore, we know that actually the circuit is inductive because the inductor is leading the... The circuit is inductive because the reactance of the inductor leads the resistance by 90 degrees. So if I draw a Phasor diagram here, we'll see. So here is our XL, this is our R value, and this is our XC. And we know that the supply voltage leads the current, therefore XL is larger than XC. The overall circuit is inductive, so therefore we can note down that XL is bigger than XC. So our Phasor diagram is going to look something like alright, so I apologize. Okay, here we go. Alright, so our Phasor diagram should look like this. So we have our impedance is right here. So sorry, impedance on our hypotenuse. And this is XL minus XC, and this is the resistance R. And we know that this is 35 degrees. This angle here is 35 degrees because the source voltage is leading the current. The resistance is in phase of the current, and the impedance is in phase of the supply voltage. Therefore, we can see that this phase diagram here, we have our impedance leading our resistance by 35 degrees. So that's our Phasor diagram, and we want to find out impedance, okay? So we know that R equals to 150 ohms, so R equals to 150 ohms, and we're trying to find Z. So in this case, we can use our Pythagoras theorem rules, okay? So we can say that cos 35 degrees is equal to R over Z, which is equal to 150 over our impedance. And remember to put your calculator on degrees because 35 degrees and cos 35, 150 bars. So you should find that our impedance is equal to 183.12 ohms, which rounds to 183 ohms to 3SF. And this could be a merit or achieved this could be a merit or achieved question. Should be a merit level question. Should be achieved for being able to draw the Phasor diagram, and merit for being able to draw the Phasor diagram and being able to calculate the impedance. Question C. The inductor has an inductance of 0.380 henries. By calculating the total reactance of the circuit, determine the capacitance of the capacitor. Alright, so we can calculate the total reactance of the circuit using a very similar strategy to how we just calculated the total impedance. We can use our trigonometry rules, okay? So we can say that, in this case, we can say that tan 35 degrees equals to XL minus XC, which is the total reactance. Total overall reactance, since XL and XC are 180 degrees out of phase. So tan 35 equals to XL minus XC all over R. So we can write that one down. So we can say tan of 35 equals to XL minus XC over R. So therefore, our XL minus XC equals to tan 35 multiplied by 150. And that should give us an answer of 105.03 ohms. So that's our XL minus XC. Right, so we know that our inductor has inductance of 0.380 henries. We can say that XL equals to 2 pi FL. So XL equals to 2 pi times 50, which is our frequency of our source, multiplied by 0.380. So that should come out to be 119.38 ohms. The inductive reactance is 119.38 ohms. We can plug that one in. So 119.38 minus XC equals to 105.03. Alright, so if we rearrange to find for XC, we can clearly find that XC should come out to be 14.35 ohms. So that's our capacitive reactance. Okay, it's 14.35 ohms. We can use that XC equals to 1 over 2 pi FC. So therefore 14.35 equals to 1 over 2 pi times 50 times the capacitance. So and we should find that our capacitance comes out to be 2.218 times 10 to the power of negative 4 farads, which rounds to 2.2 times 10 to the power of negative 4. 2.22, which rounds to 2.22 times 10 to the power of negative 4 farads, which is to 3 SF. That should be our final answer for this question. Okay, 2.22 times 10 to the power of negative 4 farads, and that should be a merit level question. In terms of getting an achieved, perhaps if you can find the overall reactant, you can get an achieved. Okay. So question D, explain what change needs to be made to the frequency of the signal generator to bring the circuit to resonance. Alright, so this question, we need to make sure that for resonance, we know that XC equals to XL. The reason that XC equals to XL is because XL and XC are directly out of phase. They're 180 degrees out of phase. Hence, the total reactance is actually the difference between the XL and XC. The resonance occurs when the overall reactance is equal to 0 ohms, meaning that XL equals to XC, meaning they fully cancel each other out to give you an overall reactance of 0. The impedance of the circuit is just equal to the resistance of the circuit, and therefore, since the impedance is at the minimum, the current will be at the maximum. The RMS current will be at the maximum in the circuit. So first we need to explain what resonance is. So we can say that resonance occurs when there is no this means that XC and XL are equal. Hence they cancel each other out. Hence they cancel each other out for X total equals 0. Seeing as they're at resonance, you can say that current is at the maximum. So you can say current RMS is. Alright, so now in terms of explaining what change to be made to a frequency, we need to see. So now first things first, we can see that XL is greater than XC, meaning that we need to find a way to reduce the XL value and increase the XC value. Since we know that XL is proportional to frequency and we know XC is inversely proportional to frequency, we know that decreasing the frequency will decrease XL and decreasing the frequency will increase XC, which is what we need since we want to decrease XL and increase XC until our XL equals our XC, which is where resonance occurs. So to put this in a sentence, we can say since so XL is proportional to F and XC equals to. So we can say that decreasing the will decrease XL and increase XC. So we can say since XL is greater than XC, so the frequency needs to be decreased. Sorry, it's pretty messy. So frequency needs to be decreased until X equals to XL. Alright, so we know we need to decrease the frequency, and then we can actually calculate the resonant frequency if we wish to. We don't have to, but to support our answer we could. So FO equals to 1 over 2 pi LC. If we plug in our numbers, this is 2L square root of 0.380 multiplied by 2.22 times 10 to the power negative 4. So this equals to Alright, so this gives us an answer of 17.3 Hertz. So you can say that hence the frequency should be decreased to 17.3 Hertz. Alright, and that's our final answer for this question, and this should give us an excellent grade overall. In terms of getting a merit, if you can explain what resonance is, the requirements for resonance, and then perhaps if you can say like XL is proportional to F, XC is inversely proportional to F, that could be enough for a merit. To get an achieved, you can just explain what resonance is. For example, XL equals XC, they're out of phase, which means that impedance is just a resistance. That, just some brief explanations about the resonance should be enough to get you an achieved, okay? So that's question 1 for electricity. Question 2, the circuit below shows a simplified version of the car ignition system. The ignition coil is comprised of an inductor of 5 henries and 22 ohms. The inductor can be modeled by a 5 henry ideal conductor. Well, I think that's meant to say inductor, not conductor. That's a typo from them. So that should say inductor. Alright, the inductor can be modeled by a 5 ohm ideal inductor and a separate 22 ohm resistor, as shown in the diagram. The 12 volt battery is connected to a switch, and the inductor and resistors are in series. The spark plug is placed in parallel with the inductor and resistor. State the voltages across the inductor and resistance the instant after the switch is closed. Alright, so we know that the instant the switch is closed, there is a very high rate of change of current. There is a high rate of change of current through the inductor, which generates a high rate of change of magnetic flux. So we know that according to Faraday's law, the size of the voltage induced in the inductor is proportional to a rate of change in current. And we know due to Lenz's law that this the voltage induced will be opposing the source voltage. So therefore, initially, there's going to be a very high rate of change in the inductor. So there's going to be a very, very high voltage induced in the inductor that's going to be opposing the source voltage. Initially, this opposition is going to be equal but in opposite directions, and therefore, there's going to be 12 volts across the entire branch. So there's going to be 12 volts. So R plus L. So we just say the voltage across the resistance and the inductor should add up to 12 volts since it's connected to parallel here. And we know that initially, there's going to be a high rate of change of current in the inductor. Therefore, the inductor needs to induce 12 volts, and there's going to be nothing here through the resistor. So if we just state that, we can just say that inductor is 12 volts, resistor is 0 volts. Okay, so explain why the current takes time to reach a maximum when the switch is closed. So with this one, you can really just say the high rate of change of current initially. So I'm just going to bullet point this one. It's going to take me a while to write out. So you can just link these few points together. So you say that there's a high rate of change. So high rate of change of current in this inductor. So that results in a high rate of change of magnetic flux. So high rate of change of magnetic flux. So then you can link that to Faraday's law. So voltage induced proportional to rate of change in current. And there's also Lenz's law. So that's voltage opposes the change that causes it. So voltage opposes change. And you can say this is going to be opposing the source voltage. So voltage induced opposes the source voltage. Say voltage induced opposes the source voltage, causing a delay. And you can say, if you wish to expand on technically you can just leave your answer like this. You can just say, link these bullet points together. However, if you wish to expand your answer, you can say that after some more time has passed, the rate of change of current is decreasing. Therefore, the magnitude of the voltage induced is also decreasing, meaning that there's less opposition to the source voltage, meaning that there's more and more current can flow. And eventually, after about 5 time constants, pass, there's going to be about no more rate of change in current, and therefore no rate of change of flux in the inductor. The voltage induced in the inductor is 0 volts. At this rate, at about a bit more than about 5 time constants, it's going to be 0 volts induced in the inductor, and all of the 12 volts is going to be in the resistor. Okay, so they kind of switch places after about 5 time constants. So if you wish to expand your answer, you can just keep linking the points, and we can link that to the graph as well if you wish to do so, but there's no need if you want to just brief out. This is enough. Just what I've written here should be enough to get you the full mark. But if you want to expand your answer, you can link this to a graph. So the current builds up like this. Initially, there's a high rate of change in current, so there's a high gradient. So this is current in time. There's a high gradient, and then after a while, the rate of change in current decreases. The voltage induced in the inductor decreases, which opposes the source voltage. Therefore, the current starts to increase. Okay, until it gets to a maximum. Okay, this is about 5 time constant here. So 5 time constant. There's going to be no more rate of change in current, and there's no more induced voltage. Question C. Calculate the circuit current 1 time constant after the switch is closed. Alright, so this question, okay, so you know that after 1 time constant, 63% of the maximum current will be reached. And you can actually just use a formula if that's easier for you to remember. So the formula that you can remember is just I equals to the maximum current. So this is current at any time, so that's I of t, okay? So let me try that again. So current at any time is given by the maximum current times by 1 minus e to the power of negative t over t, where t is the time and this tau here is the time constant. So we can just link it to this formula here. So we can say, so first you need to find out the maximum current. Okay, so the maximum current is when there's 0 volts in the, it's 0 volts through the inductor and all 12 volts through the resistor. So it's also just acting just like a simple series circuit here. So V equals to IR. So V equals to IR, and we can say that 12 equals to 22 times of I. Our maximum current is about our current is I max equals to 0.545 amps. Okay, so we can plug this one in. So we can say our I at any time equals to 0.545 times 1 minus, and after 1 time constant, t is equal to the time constant, so that's just e to the power of negative 1. Alright, if we plug this into our formula, just substitute. Alright, so we should be getting I equals to 0.3448 amps. This one rounds to 0.345 amps free SF. Alright, and for terms of the grades of this question, this should be a merit level question there. Okay, for the question C, that should be a merit level question as well. Okay, so 2 merit questions there. Question D. Spark plugs need a very high voltage of nearly 20,000 volts to produce a spark. Explain why a spark is produced when the switch is open but not when it's closed. Right, so when the switch is open, okay, so when the switch is opened, we'll just start with closed. Okay, so when the switch is closed, we know that it's connected to a battery, and then we can just explain how there's like a high rate of change of current. The inductor is going to oppose the voltage, etc. And since it's connected to a voltage, if you look at Kershaw's voltage law, you know that the voltage around any closed loop is 0 volts. Okay, that's based on conservation of energy. And because this battery is in a closed loop with the inductor, the maximum voltage that can be induced by the inductor is simply equal to the source voltage, okay? Or you can also think of it like this, okay? You can see that the resistance of this branch here is 22 ohms, and you know that the time constant equals to L over R. And since our resistance here is 22 ohms, and this is going to give us a pretty high time constant, which means that it's going to take some time for the current to build up. And we know that the voltage induced by the inductor here, so that's E equals to negative L di over dt. Since it's a very big time constant, okay, so the size of the voltage induced against the source voltage is actually not that large. It's not going to exceed 20,000 volts, okay? It's because for a spark to be produced, it needs to be 20,000 volts to produce a spark. But since it's going to be a very, very high time constant, it's going to be unable to induce such a high voltage. And you can link that to also that there's the battery connected to the inductor, which means that the maximum voltage induced by the inductor is actually just the 12 volts of the battery. When the switch is opened, you see it's disconnected to a battery, okay? And when this happens, we know that the voltage is no longer limited to the voltage induced by an inductor is no longer limited to the source voltage because it's no longer connected to the source voltage. So Kershaw's voltage law does not limit us anymore. And also we know that the spark plug here, so once we disconnect, we have our spark plug here, is a free open space. Free open space means that there's a very, very high resistance. Very, very high resistance means that this R value is very, very big. If this R value is very, very big, we know time constant is inversely proportional to the resistance, which means that there's going to be a very, very low time constant, which means that so once we open the switch, okay, there's going to be a very, very high decrease in current in the inductor. The inductor is going to try to oppose that change by inducing a current that's in the same direction as the source was originally. However, this current is going to collapse to 0 very, very quickly. And the reason it collapses to 0 very, very quickly is because the time constant here is very, very low. And because it's a very high rate of change in current, the change in current is very big because there's a high collapse. So if we look at the graph here, when we build up the current, when this switch is closed, when we build up the current, the graph looks like something like this. However, when we open the current, it's going to look more like this when we go down, okay? So that's what it's going to look like, okay? So we're going to have a slow buildup of the current when the switch is closed. When the switch is open, the current's going to collapse to 0 very quickly. There's going to be a high rate of change in current in the inductor. It's going to result in a very high EMF. And this high EMF is obviously not going to be limited to the source voltage, and it's going to be larger than 20,000 volts, which results in the spark being produced. So those are the basic points we needed to cover there, okay? So we can say that when the switch is closed, so the inductor is connected to the source. So according to Kershaw's voltage law, sorry, I cannot spell, sorry, to Kershaw's. So therefore you can say that the voltage So we say that the voltage induced by the inductor is purely limited to the source voltage, so the E must be less than or equal to 12 volts, okay? So this is obviously a lot less than 20,000 volts to produce a spark. And also you can say that is high time constant. Okay, so since the inductor branch, the time constant equals to L over R. Yes, L over R. Okay, so that's our time constant. So time constant equals, we can actually calculate our time constant. We have our L, which is 5 over 22, which equals to 0.227 seconds. So this is very high. And since E equals to negative L di over dt, the induced, we can just say that the rate of change of current is low. Resulting in a low induced voltage. You can say no spark, okay, no spark in this case. In terms of when the switch is open, you can just go and explain how it's, okay, so I'm just going to bullet point it, okay, so since I'm running out of space here, I'm just going to bullet point the second part. So bullet point, I'm going to say, so no longer connected to battery. So you can say that there's high resistance due to the open space. High resistance due to open space. So you can link that to a low time constant. You can say that current collapses to 0 very quickly. Current collapse. And that you can link it to a high induced voltage, and hence there is a spike. Alright, so those are basically the points we needed to link first. We needed to explain why we cannot have a high voltage induced when the switch is closed, and why those limitations do not exist when the switch is opened, okay? So if you can link both of those together, you'll get an excellence. If you can describe any one of them, you should be able to get a merit. And achieved is usually just like bullet point, like if you can just briefly explain, like maybe just half explain it, you can get an achieved, okay? So half explaining can get an achieved, okay? So let's look at our final question here, question 3. Disposable camera flash. Capacitors are commonly used in electrical circuits to store and dissipate energy. In a disposable camera, a capacitor is charged by a battery. This energy is used to flash the bulb while the photo is being taken. One such disposable camera uses a 1.2 times 10 to the power negative 4 farad capacitor. The camera is supplied with a battery of EMF 3 volts with no internal resistance. A simplified diagram of the circuit provided is on the right. So switch A is closed and switch B remains open. Sketch a graph in the space below to show what happens to the size of the current over time as the capacitor charges. State what determines the size of the maximum current. Okay, so in terms of drawing the graph, okay, since we don't know this resistance here, they're not telling us this resistance here, we don't know the time constant, so we actually don't know the time constant. So as long as we have the correct shape, it should be okay, okay? We just need to have a decent shape. Right, so we know that initially there's going to be a very, very high current, and then since there's going to be a build-up on charge on the capacitor, this build-up on charge is going to cause a pushing voltage against the source voltage, and that charge builds up over time, meaning this voltage here increases across the capacitor, increases over time, which opposes the source voltage, causing the current to decrease exponentially. So this is our current here, that's our time, so it should look like an exponential decrease, okay? Pretty hard to draw on a device, but it just look like an exponential curve downwards. Alright, so apologies for the bad drawing. It's pretty difficult to draw on the device, but you should see that it's an exponential curve downwards. So what determines the size of the maximum current? So the two things that determine the size of the current, you can just say V equals to IR. So that's the source voltage. And the current, so not current, that's affecting, you need the resistance, okay, resistance. So that's the resistor, this is the size of the resistance. Right, so question B, calculate the, so that should be just an achieve level question, to be honest, since we're not drawing the graph with specific values or anything, we're just drawing the graph with drawing the graph to just a shape, so that should just be an achieved. Calculate the energy stored in the capacitor once it is fully charged. Compare this with the energy supplied by the battery and account for any difference in the energy. Alright, so we know that the energy stored in the capacitor is half Q times V. Alright, or we can just rearrange this, and we can also say that it's E equals to half CV squared. So therefore, E equals to 1/2 times the capacitance, which is 1.20 times 10 to the power negative 4, times the voltage squared. So the voltage is equal to the source, which is 3 when it's fully charged. So 1.2. Which equals to 5.40 times 10 to the power negative 4 joules. So now we need to calculate the energy stored in, the energy given by the battery. So first of all, this is capacitor, and this is battery. So we know that the voltage is defined as the energy given to each coulomb of charge. So energy is the energy given to each coulomb of charge. Okay, so that's a voltage, sorry. And we also know that voltage is energy given to each coulomb of charge, and we want to find out how much charge is given. So we're going to be finding the total amount of charge that's on the capacitor plates. Okay, so total charge, you see that Q equals to CV. Q equals to 1.2 times 10 to the power negative 4 times 3. Which gives us 3.6 times 10 to the power negative 4 coulombs. And we know that the voltage is 3. Okay, so voltage is 3. That's the amount of energy given to each coulomb of charge. As we can see, it's here. So we're going to plug that one in. So 3 equals to energy, total energy given, times the amount of coulombs of charge, times 3. And therefore energy is 1.08 times 10 to the power negative 3 joules. As you can see, the energy of the capacitor, energy stored in the electric field of the capacitor is half the energy given by the battery. This reason, so half the energy is lost. Half of the energy lost to not internal resistance, what am I saying? Okay, half the energy is lost to heat. This is dissipated in the resistor, so lost to heat. Alright, so half the energy is lost to heat dissipated in the resistor. This is a merit level question, okay, achieved for finding the energy and merit for the reasoning as well, okay. Emily decides to investigate the capacitors further. She uses a sheet of plastic insulator with a thickness of 2.00 times 10 to the power negative 3 meters and a relative permittivity of 10 by placing the metal foil on each side of the plastic sheet to make a capacitor. Calculate the area of the metal foil on each side of the plastic sheet Emily will have to use in order to get the same capacitance as the camera flash. Okay, so we know that the capacitance equals to E naught ER times A over D. Okay, so that's our relative permittivity, so that's our constant there. That should be on our formula sheet. And we can say that capacitance is 1.2 times 10 to the power 4 equals to 8.85. Multiplied by 10, multiplied by our area, we don't know, all over the D, which is 2.00 times 10 to the power negative 3. Alright, so we should find that our area equals to 2711.86 meters squared. We can round that down to 2,710 meters squared 3SF. Alright, that should just be an achieved level question if I'm being honest with you. Okay. D. Emily experiments with two capacitors by pre-charging them and then connecting them in parallel. She takes the 1.2 times 10 to the power of negative 4 farad capacitor and charges this to 50 volts, and she takes the 1.00 times 10 to the power of negative 4 farad capacitor and charges this to 40 volts. He then connects them in a parallel, such as the positive plates are connected together. Alright, so for this question, we need to describe the direction of the motion of charge once the capacitors are connected together. Alright, so we know that charge always flows from a high potential to a low potential. So therefore, the 50 volts is a high potential, the 40 volts is a lower potential. Therefore, the charge is going to start falling from plate number A to plate number B. So therefore, the direction of the current is going to be in this clockwise direction. Okay, it's going to flow from plate A to plate B. And this is because plate A has a high potential and current always flows from high potential to a low potential. And this is going to happen until both of these plates have the same potential, and since there's the same potential, no more charge is going to flow, and that's when we say that the equilibrium has been reached. Alright, so if we want to describe the motion of charge, we can say that current flows from high potential, high to low potential. A has a high. So hence charge flows from A to B. And we can say this is clockwise since it's clockwise direction. So clockwise direction. Alright, so this question, okay, it gets a little bit challenging. Okay, so we know that after at equilibrium, the voltage at A is equal to the voltage at B. Okay, so that's what we know at equilibrium. Okay, so first things first, we should figure out how much charge is on A and how much charge is on B. Okay, we can do that very simply by using Q equals to CV. So for A, so Q of A equals to 50 times 1.2 times 10 to the power negative 4. So 1.2 times 10 to the power negative 4 times 50. This gives us 6.00 times 10 to the power negative 3. So 6 times 10 to the power negative 3 coulombs. For B, we have 40 times of 1 times 10 to the power negative 4. That gives us 4 times 10 to the power negative 3 coulombs. Alright, so since we know that charge cannot be lost, okay, so we have a conservation of charge concept here. Charge cannot be lost or destroyed. It's going to be transferred from plate A to plate B. So the charge lost by A is equal to the charge gained by B. So charge lost by A equals charge gained by B. And then we're going to call this x, okay? We're going to call this x variable, okay? Let's go to the other side of the page, okay? Alright, so we know that the voltage A is equal to voltage at B, and we know that Q equals CV, so Q over C equals to V. So V of A obviously equals to charge of A over capacitance of A. V of B equals to Q of B over capacitance of B, okay? And QA, we're going to define it as Q, so we have our initial charge is this, 6 times 10 to the power negative 3 coulombs, minus some X amount of charge is going to flow off the plate, we don't know how much that is, divided by the capacitance, which was 1.2 times 10 to the power negative 4. That is equal to the charge gained by B, which is initial charge plus X, so 4 times 10 to the power negative 3 plus X all over 1 times 10 to the power negative 4. We can cross multiply here. Alright, so we should get 6 times 10 to the power negative 7 here, minus 1 times 10 to the power negative 4x equals to 1.294. 4.8 times 10 to the power negative 7 plus 1.2 times 10 to the power negative 4x. Alright, so now we will get 1.2 times 10 to the power negative 7 on this side. If we move all the x's to one side, so 2.2 times 10 to the power negative 4x. Alright, so we should find that x equals to 5.45 times 10 to the power negative 4 coulombs. Alright, so that's the amount of charge lost by A and the amount of charge gained by B. So if we want to find the equilibrium voltage, we can just say VA equals to 6.00 times 10 to the power negative 3 minus 5.45 times 10 to the power negative 4 all over the capacitance. Oh, sorry, oops. Oh, dang it, sorry. Minus 5.45 times 10 to the power negative 4. Alright, so that gives us a voltage of 45.46 volts, which rounds to 45.5 volts, 3SF. Okay, so that's the answer given. We showed it, so QED there. So we've showed this is true. And the charge at A, the charge is equal to 6.00 times 10 to the power negative 3 minus 5.45 times 10 to the power negative 4. And that should give us 5.455 times 10 to the power negative 3 coulombs. If we round it to 3SF, we'll get 5.46 times 10 to the power negative 3 coulombs. So that's the final charge on A, and that's our final answer, and this should be an excellence level question. If you can get your explanation and your final charge correct, that's an excellence. To get a merit, you probably need to find the voltage. If you can find the voltage and the explanation, you'll get a merit. To get an achieved, if you have a correct explanation of the direction of current flow, you should get an achieved. Okay, so achieved should be here. Alright, so thank you for watching this video for the level 3 electricity paper. Hope you enjoyed, and I'll see you all in the next one.